Scientific model often changes when we make new discoveries. Today we will see how the discovery made in Thomson and Rutherford's experiment led to significant changes in the model of the atom. Prior to the discovery of the electron in 1897, the model of the atom had not changed much since its inception by the ancient Greeks. The generally accepted model of the atom had been proposed by John Dalton in 1803. This model was based on Dalton's own scientific experiment with the gaseous compounds and Antoine Lavoisier's law of conservation of mass, as well as Joseph Proust's law of constant proportions. Given the robust and predictable behavior of matter described in these laws, Dalton proposed all matter to be made of atoms were indivisible, invisible, and independent particles. They are often represented as solid balls which hook together to form substances or compounds.
In 1897, J.J. Thomson used a device known as a cathode ray tube to disprove Dalton's model of the atom through the discovery of a subatomic particle, namely the electron. The cathode ray tube was developed by Sir William Crookes in 1870. He was able to develop the cathode ray tube thanks to the invention of the Ruhmkorff induction coil by Heinrich Ruhmkorff in 1851 and a powerful vacuum pump by Crookes' co-worker Charles Gimmingham in 1872. The cathode ray tube consisted of a glass tube that was evacuated using Gimmingham's vacuum pump to pressures less than a millionth of an atmosphere. It also consisted of a negatively charged electrode known as a cathode and a positively charged electrode known as an anode. An extremely high voltage could be applied across the electrode using Ruhmkorff's induction coil, resulting in a green glow or ray which emanated from the cathode. This was known as a cathode ray. The main purpose of Thomson's experiment was to determine the nature of this cathode ray. At the time, it was known that a charged particle experiences a force in the presence of an electric field. By applying an external electric field, Thomson realized that the cathode ray deflected towards the positive plate. This meant that the cathode ray consisted of negatively charged particles. It was also known that magnetic fields act upon moving charged particles, and so Thomson applied a magnetic field to the cathode ray. He determined that at a given magnetic strength, the magnetic force acting on the cathode ray cancelled out the force the ray experienced due to the electric field, resulting in an undeflected ray. By noting the ratio of electric field strength to magnetic field strength required to achieve this, Thomson was able to calculate the velocity of the negative particles in the cathode ray. By using this calculated velocity, Thomson was able to calculate the mass to charge ratio of the negative particles. He discovered that the ratio was over 1,000 times larger than a charged hydrogen atom, the smallest atom known. Thomson's colleague then determined the size of the charge of the negative particle was equal to that of a charged hydrogen atom. This meant that the particles in the cathode ray had to be over 1,000 times smaller than an atom. That is, the cathode ray consisted of negatively charged subatomic particles. Regardless of the type of metal used at the cathode and therefore the type of atom, Thomson achieved the same results. Therefore, Thomson concluded that these subatomic particles were present in all atoms. From this, he proposed a new model of the atom. His model consisted of small negatively charged particles, later to be named electrons, embedded within a positively charged soup. He likened this model to a plum pudding, where the negative electrons represented the raisins in the pudding and the dough contained the positive charge.
The plum pudding model of atom wasn't around for long, as it was potentially replaced by Ernest Rutherford's atomic model in 1911. Rutherford performed an experiment in which he used fundamental technology like the alpha particle emitter to fire alpha particle at a thin layer of gold foil to observe how the trajectory changed upon interaction with the atom in the film. Changes in the trajectory was observed by viewing a fluorescent screen which emitted an isolated flash of light when hit by an alpha particle. Based on a Thomson model of atom, Rutherford expected an alpha particle to pass through gold foil without deflection, as there was no dense object or area of concentrated charge of the atom. Rutherford observed most particles pass through foil without deflection as expected, but he also observed some particles experience deflection at different angles. Given this result, he produced his own atomic model. This model consists of a densely positive charged nucleus with the electron that circulates around the atom at some fixed distance. Overall, rapid changes in the accepted model of atom illustrate how scientific discoveries had this significant implication on our scientific understanding, as well as the model we use to understand complex phenomena.